Okay, so we learned summation notation yesterday. Was this brand, I mean, this is kind of what BC said. A lot of them felt like this was brand new. They'd never seen this before. This summation notation, this capital sigma. Brand new? Okay, oh, physics. Okay, so all right, so it wasn't, not in calculus, yeah. Hmm. Yeah, oh, okay. Yeah, that makes sense, right? Because if you think about what you're doing with an average, you're adding up a bunch of squares. So like you're right, in Excel or a Google Sheet, you could use that notation to say like add up all of the like A, so like column A, A K through, I don't know, column A, row K, and the sigma would say, count through those. Like I said, if anybody has any programming experience, it's very much similar to like looping through something. But it's just our notation we use in math for that. This is telling us to start at K, count up by 1 until we get this number. You can then, by using expressions inside here, you can actually, the physical thing, the number that you're using doesn't have to necessarily be 1, 2, 3, 4. If you're doubling K in here, you would actually like sort of count by the even numbers. So there are different ways that you could play with it. But in the end, it really is just notation for us, especially in AB. So the last unit in BC, which if you take Calc 2 in college, you'll see this too. The last unit in BC deals with series, which are infinite sums. So sums very similar to what we're doing here, where you're repeating it an infinite number of times. And if you look at our definition on the board, that is what we're doing. We're taking the limit as we have an infinite number of these, in our case, rectangles that we're trying to find the area of. What we're also doing is, because we've got our fixed width, if we're doing an infinite number of rectangles, we're really squeezing those bases in to be we call it infinitesimally small. So those, the more rectangles you have, the thinner those bases get. If you're approaching an infinite number of rectangles, your base size is approaching 0. Does that make sense? Kind of from the physical picture that we've been looking at. And that's what's going on there. And again, a lot of this is just the notation for integrals. Back with derivatives, we had all of that algebra, those big algebra problems that we had to solve because we could actually compute the limit. But here we just need to identify that the limit is an integral, and then we'll solve the integral. So we kind of looked, like I said, I was hoping that you guys got 75% out of what was going on here. We did a physical example. There were sort of 3 things we had to look at. We needed to know what our width was each time. We computed that. We had to figure out what x value we were plugging into our function, and then we had to figure out what our function looked like once that x value was plugged into it. So we did it in a specific case where our function was the square root of x, and then we did it in a general case where our function was just a function. It was f of x. In the end, that's how we developed that formula that you have on your card, which is basically the sum of the areas of a bunch of rectangles. Delta x represents the width of your rectangle. Like I said, that's a capital delta, Greek letter, capital delta. Anytime you see this, it means the amount of change of x. Okay, so delta anything is the amount of change of that something. So it was how much we changed in x terms from rectangle to rectangle. That was our base, and our height was basically plugging this x value in to our function, and that x value is a or bigger, so we write that x value as a plus delta x times how many rectangles we went over, right? If delta x is 0.5 and we go over if delta x is 0.5 like it was over here, and we go over 3 rectangles, we are 1.5, 3 times 0.5, past a. That's where that a plus delta x times k is. The k represents what rectangle you're on. This is real math that we're doing, by the way. We've hit like real math. You're seeing a difference between the things that you've learned in the past and, higher level calculus. Okay. Putting that all together, bases, heights, areas, multiply them out. This piece I skipped over yesterday, kind of purposely. We had talked about a lot. There were probably a lot of things swimming in your head. The only thing that we were saying here is our whole analysis up at the top was done with a right sum. We could do that exact same thing with a left sum. There'd be a couple pieces that would be a little bit different in the middle, but the ideas would all be the same. A couple different ways that might show up. If I do a left sum, think about the right sum. Let's actually look at a right sum. So think about my right sum. My first rectangle has a height that's evaluated with this x value, right? So I have to do a plus delta x in my first to get my x1, right? Think about the left sum. The first rectangle has a height that's determined by evaluating f at a. So I don't need to add delta x to the first rectangle. So one way to solve that is by not starting my index at 1, but starting my index at 0. So this one on the left is an example of a left sum, which is not what we did yesterday. But the difference is the index value starts at 0. So your first rectangle, a plus delta xk, is a plus delta x times 0. So that little change, counting from 0 to n minus 1, instead of from 0 to n, gives you a left sum. Because basically what you're doing is each of your individual rectangles is starting at an x value that's 1 delta x less than it would have been in the right sum. Another way to do that is actually to subscript the x a little bit different. So still count from 1 to n, but do x of k minus 1. So you'd actually do x of 0. In both cases, look, your first thing would be x of 0. Here, it's physically 0 because my index starts at 0. Here it's 0 because I wrote x of k minus 1 instead of 1. That being said, the idea there is if you see notation that looks like this, even if there are, a couple little things different in the summation, it could just be that they're doing a left sum instead of a right sum. Okay? All right. If things go different in the middle, then we're going to see that today. Okay, so let's look at our remaining examples. I think the one that we left on, this one actually I think is even easier, but it does bring out a really good point. In order to turn an integral into its limit definition, we need to know what delta x is and we need to know what xk is, right? Those are relatively easy to figure out, especially delta x. What is delta x in this example? It's not just pi. Pi is the full width of the interval, but we're breaking it into n rectangles. So what's the width? Correct, pi over n. So it's always nice when our lower limit is 0 because our overall width is just the upper limit. Right, Dan? Yeah. But then we have to divide by n because that's what we're doing. We're breaking it up into I don't want to say unknown because our goal is to break it up into an infinite number or take the limit as we break it up into an infinite number. So that n is the increasing number of subintervals we have. Xk is just a plus, this is a formula to remember, a plus delta x times k. So a in this case is 0, so I don't even need to write it. Delta x we already know is pi over n, and then I just need to multiply that by k. Yep. And now we can get to writing out what our integral equals. It's the limit as n goes to infinity. We want an infinite number of rectangles. We are taking the sum of each of those rectangles' areas. We're going to start at 1. We're going to go to n. The height of each rectangle is going to be f of xk, our function, which is sine of x over 2. So that's going to be the sine of pi k over n divided by 2. So I can say pi k over 2n. Say that again. That's just a typo on my part. Good catch, though. Yeah, I didn't want to make it any different. No, I didn't want to even read those directions. Yeah. Yeah, if it was left, I'd have to go from 0 to n minus 1. That would be the only difference. But I don't want to get into the weeds with that stuff. So that is the height of my rectangle, and the width of my rectangle is delta x, which is pi over n. I want an infinite number of tiny width rectangles. I want to add up all their areas. Each one has an area of the function evaluated at the correct x times the width, which is the same for each and every one of them. Sound good? What I want to point out in this one, which let's take a look. What did we have here? We had limit. I need this up here to compare. Sum k equals 1 to n. We had -2 plus 2k over n, right? Plus 3, yeah, plus 3. Squared times 2k over n. Or just 2 over n, no k in the delta x. Okay, all right. So the reason that I want to point this out, because in the next section, we are going to go in the opposite direction. Delta x shows up in two places, right? Very similar. Like in this one, there's your delta x 2 over n. There's your delta x 2k over n. So you can look at both of these and say, oh, my delta x is 2 over n. You've got to be careful when this happens. Here, it appears that my delta x is pi over n. Here, it appears that my delta x is pi over 2n. But the 2 is part of the function, not part of the delta x. So when you're looking to identify delta x, the best way to do it, and we're going to see when we get to our last example that there's options here, but the best way to do it is to look for the one without the k, call that your delta x. Anything extra going on in your function is, anything in your function part is part of the argument of the function, not part of your delta x. Okay, we'll see that. We'll see that in some examples here. Not example 1, because there we go. We've got 5 and 5. Here we have 4 and 4. I think example C is where we're going to get it. Okay. All right, so next thing we're going to do is we're going to reverse this process. So we want to identify a delta x, xk, and then f of x, and then we want to write the definite integral. So let's start with delta x. What's delta x? 5 over n. Yep, I agree. There's my delta x, 5 over n. What's my a? 2. Correct. Yep. So the idea here is we're actually sort of identifying our xk as this. There's our xk. There's our delta x. Inside of our xk is a plus delta xk. That's what makes our a2. So then what's our b? Remember that delta x is telling you how wide your interval is. So b never shows up anywhere. You have to figure it out. But if you're starting at positive 2 and your interval total width is 5, then b is 7. Yep. Boom. So this, I think we're there. I guess I did ask you to identify x sub k, which we did. I just highlighted it in there. So that works. So we have the integral from 2 to 7. Xk becomes x. So I have 5x minus 1. Yep. And then dx. Delta x becomes dx. You have to know which axis the rectangle bases are on, and that's what the dx is telling us. Dx is telling us, and it's, delta is the Greek letter, capital D, and we use a D for dx. So we're trying to be consistent at least with which letter we're using. So when we're talking about an actual measurable amount here, which is, if I have n subintervals, I can figure out what that width is. When we're in the integral, we're talking about an infinite number of subintervals, so we use a slightly different notation. We use the little dx. That is an infinitesimally small amount. All right. Questions on that? No? All righty. Letter B. That is a left, correct. So I started k equals 0. I went to n minus 1. That doesn't change anything we have to do in this problem. It just happens to be a left sum. It turns out that no matter whether you use a left, right, midpoint, or trapezoidal, if you wrote this limit out, you'd get the same value for that limit, no matter which one you use. And that's why we don't care. The left limit goes to the right limit, the trapezoidal limit. They all approach the same when you go to an infinite number of rectangles, or I guess an infinite number of trapezoids if you're doing trapezoidal. Okay. So we need our delta x, which is, yep. Got that. We need our a, so we need our x sub k, which looks like what has the form. So remember that xk is of this form, a plus delta x k. So we've got to be in that form somehow. Right. Yeah, so think about it that way. Because it was minus, the two things are switched. But, if I was writing it in this form, I could write that exponent on the e as -1 plus 4k over n. So there's your xk. Which makes our a -1 and our b 3, right? -1 plus 4. So 3. Yep. So we have the integral from -1 to 3 of 2 e to the x, yep, dx. Boom. 2 e to the xk delta x, 2 e to the x dx. They do really have the same pieces in them. The integral is taking the place of the limit and the sum, just all kind of going into one. All righty. Okay, I guess hopefully if it doesn't show up in this last example, I'll go over it before we go over it. I'm thinking out loud. Okay, our last example. This is the one where things are going to get a little bit weird. Oh yeah, we've done a couple. I've done a couple things here. First thing here, just like Ivan said on this one, this is a left sum. This is one way we get a left sum. Because we want to multiply, instead of multiplying delta x by 1, 2, 3, 4 all the way up to n, we're multiplying delta x by 0, 1, 2, 3, 4 all the way up to n minus 1. This k minus 1 here also makes this a left sum. So the minus 1 isn't part of what we're doing. The minus 1 isn't part of the function. It's just making this a left sum instead of a right sum. So the first k that we're essentially multiplying delta x by here is 0, left sum. The first k that we're eventually multiplying delta x by is still 0. As a matter of fact, I could rewrite this limit, and maybe this is probably the best way to do it, just to completely get rid of that. Let's convince ourselves that these two things are algebraically equivalent. I'm going to change it to look more like the left sum that I like. And now, because I'm starting at 0 instead of 1, I can just go with k there. ln of 4k over n times 2k. if I plug 1 in here, my first term, I'm multiplying 4 times 0. If I plug 0 in here, my first term, I'm multiplying 4 by 0. It's 2 over k. Yeah, sorry. Thank you. Yeah, and there's a closed parenthesis there. Yep. Yep. Sorry. My brain had already moved on to what I wanted to say next, and I just got sloppy. Cool. All right. We are going to have to rewrite this one more time because look what we have. What's our delta x? 2 over k. Yeah, our delta x is definitely 2 over k. But we don't have 2k over n here, so we've got to rewrite this so that we actually have 2k over n. So we'll do one more. Limit as n goes to infinity, the ln. How am I going to make this say 2k over n? I like what you said. I times it by 1/2, but if I times it by 1/2, I'm going to change it. So I want to rewrite it so it's equivalent. So yeah, I think you answered my question, but I need to do it a little bit differently. I need to make something equivalent to 4k over n that has a 2 over n in it. I think I wrote k there. I had n there originally. What's another way to write 4k over n so that you have a 2? I think actually these examples, yep, I'm realizing it. My examples had k's. That's where my mistake was. These should always be n's. That's just a typo on my work there. Sorry about that. That's why I was copying those. So I need to have this. Let's do it this way. I need to have this, right? I need to have 2k, change all of them along the way. It's easy. They're so generic. I need to have 2k over n, right? There we go. So they match. There you go. Yeah. Now I think seeing it physically, that's what's got to happen here. Now I'm equivalent, right? On the left, I have the ln of 4k over n. On the right, I have the ln of 2 times 2k over n. In both, I have 4k over n, right? Okay. What's my a? Easy. 0. What's my b? 2. So I've got here the integral from 0 to 2 of the ln of 2x. Yeah. I have 2xk here. So it's 2x and then dx. So that's how you have to work it when your delta x doesn't match your xk. You've got to sort of just, you've got to make it equivalent. So how am I going to get a 4 into a 2? Make it 2 times 2. Okay. Cool. Yeah. And Ivan, you notice we didn't use the 1/2 there because if I just put a 1/2 in there, then I would have to balance that out somewhere. You know what I mean? I needed to actually get just 2 equivalent expressions in there. I liked your answer, and it seemed like it made sense, but I need to have equivalent expressions here. And I wasn't like doing a solving set of steps. Okay, last but not least, this is based on an AP question at the end. This hits the point. If you can do this, you can do anything. We have a right sum. We're going from 1 to n, and we just have k. So we have a right sum. So life is easy there. We don't have to do anything, mess with anything that we have to do in C there. There's actually 3 different integrals that this could represent. One of those integrals, the lower limit is 0. The second integral, the lower limit is 1. And the third one, the width of the interval is actually 1, as opposed to 3, which is what we would probably have done right now. Okay. I think if we were going to do any of them, we would probably do B. B would be the thing if I just said, hey, what integral is this? We would pick B. So let's do B first. We'll adjust to A. I think A is a really easy one. And then I kind of have to show you something for C. So B would be what we would generally do. What's my delta x? 3 over n. What's my a? 1, right? They actually gave it has to be 1, which makes my b 4. So I have the integral from 1 to 4. A plus delta xk is 1 plus 3k over n. So it's basically the integral of x squared. Yep. Dx. Yep. The problem, now when we jump over to letter A says the lower limit is 0. So we're going to keep our delta x 3 over n. There's nothing that told us we couldn't do that. But now we've got to make our a equal to 0, which is going to lock our b as 3. Yep. So what's our xk? Let's actually write that out. Maybe we'll write it out in both here. In this case, xk was 1 plus 3k over n. Yeah, in this case, it has to be just 3k over n. So we have the integral from 0 to 3. Now look at our function. Our function isn't just xk squared. It's 1 plus xk squared. Dx. So those two, A and B, give you an example of where you have some options with that A. Is that A the actual, the number that you see being added to your delta xk? Is that the lower limit, or is it part of the function? And it turns out it could be both. These two integrals, there shouldn't be a k there, sorry. I was saying xk when I was pointing, but there's no k in your integral form. Those two integrals would evaluate to the exact same thing. Both those integrals have the exact same value. Letter C is probably the tricky one, but we'll see how it works. We want the width of our interval to be 1. So that's going to change our delta x. What's our delta x if the width is 1? Yeah, 1 over n. So that actually means that I have to change something in here because I have 3 over n. Okay. This represents a sum, so it's something plus something plus something plus something plus something. Every one of those somethings is something that's got a 3 over n in it. You could factor that 3 out. Okay. So I can rewrite my limit as the limit as n goes to infinity. Actually, I can factor it out of the sum. And then the limit rules we learned all the way back in Unit A says that a constant can get factored out of a limit as well. So I can actually write this as 3 times the limit as n goes to infinity of the sum of k equals 1 to n of 1 plus 3k over n times 1 over n. The only time I'd have to do this is if I was trying to match it to something that they gave me. I wouldn't normally do this. I'd normally just be happy to do B, most likely, or even if my brain went in a weird direction to do A. This I'm doing because I'm matching something, right? So I have, now we have that same issue we had up in C. Our delta x is 1 over n. So we kind of want to, we don't want to think of this as, our delta x times n. We have that 3 in there. 1 plus 3xk, right? Yeah. Our xk is k over n. Or do we want to do, actually, sorry, so actually we have a choice here. Do we want our xk to be, oh, no. All right, no, our xk has to be k over n. So we're going to think of this as 1 plus, I'm going to rewrite that so the 3 is out in the front. This one always throws me, too. There it is. Yep. So I just erased 3k over n and made it 3 times the fraction k over n. So our integral here is 3 times the integral. We actually have a coefficient in front of our integral. Our xk is k over n. I think I may have missed a squared when I was writing this, right? That parenthesis was squared, so it still is squared. So if this is our xk, what's our a? 0, yep. Yeah, if there's no number, if xk doesn't have a plus or a minus, then your a is always 0. That makes our b equal to 1, because our interval width is 1. 0 to 1. And then we get 1 plus, so yeah, since this 1 is part of our function, it's not our a, so we've got 1 plus 3x squared dx. If you use the fn in on your calculator and did any one of these, they would all come out to the exact same result. If you did the power rule, which we've learned in E4, on either of these, you would get the same result. This would be the power rule, but you'd have to linear chain it in the process. So a little bit more to that one. But anyway, they all would give you the same results. Okay. All right. So as far as the what you would expect to see on the quiz or the test, things like A, B, and C are fair game. I'm not going to drop something like this part, letter C, with you on the test. Okay, that I'm not going to do. But yeah, A, B, and C are fair game. Knowing how to do this thing with getting the delta x and the delta kx to match, that's something you'll have to do. Today's yeah, mine doesn't match here, which is weird. I don't know what the heck which is good. So I can't show you what I want you to do, but that's okay because you have the right thing. I literally don't know where I know where it is. So I printed out the right thing for you, but I just don't have it in PDF form to show it on the board. But I do have it in Word form, so I can do that. E3, cool. All right. So there are some desmoses that go along with this that will let you sort of check your answers. Show you how it works. So you are going to, in the first part, you're writing, after you get past problem number 1, which wants you to write the notation of a finite, like you're not doing a limit in this one. You're actually, this is sort of like example 3a in number 1. But once you get to number 2, what we want to do here is, after you write, I feel like I need like a second to breathe so that I could come up with coherent sentences. Got it. After you write your limit, you're going to go to this Desmos. Desmos is going to have a spot, I'll click on it, where you can plug this function in and then plug your answer in. Desmos won't do a limit as n goes to infinity, but you can make that n really big, and then that really big n should estimate it. So let me click on that. It's not letting me do it with my pen. I'll show you what I mean. I actually think the answer to number 1 might even be already programmed in here. Yeah. Okay. So problem number 1, your function that you were given is 2x plus 1. They want you to write the integral from 1 to 5. So this is all set up for you. You'll have to change these when you get to the next problem. This is where you put your answer. So this should be what you come up with for your answer for number 1. I don't think any of you guys will have a hard time doing it. Just be really careful that all of your parentheses match up. I feel like I'm going to make a quick edit to this because I definitely edited it and didn't save it. What will also be here will be the actual integral. So the actual integral value will be here as well when you guys click on this. So just wait a minute to click on it. Let me update it. The actual integral value will be here, and you can compare. You should get something close. The actual integral value is 24. This comes out to 24.00016. That's because you're only doing the sum from 1 to 100,000. The integral is the limit as n goes to infinity. 100,000 is a big number, but it's not anything compared to the limit as n goes to infinity. So that's what's going on there. So this is a way for you to check to see if your Riemann sum works in sort of two ways. Did you get the same result? Again, there'll be an integral here in the minute. I just have to figure out why I didn't save, but I'll definitely get that fixed. There'll be an integral here in a minute, and as long as they're close, then you have the right thing. But it also does show that I didn't just make all this stuff up, right? Like if the integral is giving you pretty close to the value of this sum, then yeah, this stuff actually works. So you'll be able to check your answers, and it's proof on my end that I didn't just make up a whole bunch of nonsense to say, what can I tell them is true? No, this actually does work. Make sense? Okay. So number 1 is like 3A. For 2 through 5, you can check your work on there. The last 4 problems on the last page are the opposite direction, and each one of them has its own Desmos, and they are all posted on Google Classroom. So I think that saves you from having to save. I did this a couple weeks ago. I'm pretty sure that saves you from having to type in this every single time on those problems, which is in some of them a little bit complicated. Okay. Cool. So we got 20 minutes, 15, 20, a little bit under 20 minutes to get some stuff done. I'm going to update that, see where I went wrong. Might have to update the link. Dylan really wants to show me his D8.